We've talked about adding HBr across the double bond, but there are other acid electrophiles that you can add as well. So in addition to HBr, the other halogen acids you can use are HCl and HI, where we have Markovnikov addition of H and X. So if we look at a double bond and you add, instead of HBr, maybe we add HI to that, then we're going to add this in a Markovnikov fashion, meaning the H will go to this carbon, because this carbon has 2 hydrogen on it. The I will go to this carbon, because this carbon only has 1 hydrogen. It's more substituted. So then the product, if you want to draw the H in, it's right here. And the I is there. Again, we can always simplify these and leave the hydrogen implied. And just draw the product like this. In addition to those acids, we can add acid and water. And you'll notice that I have a few different ways this is written. You can write it as H plus and H2O, sulfuric acid and water, or H3O plus. These all basically mean the same thing. And if you see any of these are going to be Markovnikov addition of H and OH. So the OH comes from the water. So let's look at the product for that, and we'll talk about the mechanism here in just a second. Here's our alkene. Now I'll just use H3O plus. What we're going to end up with is the Markovnikov addition. Hydrogen will add here, OH here. And again, if you want to simplify it, without the hydrogen, you can do that. Our third option is very similar to the acid and water, but we're adding an acid plus an alcohol. This is also a Markovnikov addition. Of H and OR, where OR is whatever R groups on your alcohol. So let's say we do the top case where we have methanol. I'm going to use the same alkene and add H plus and CH3OH. And in the product, I end up with a hydrogen added to the less substituted side, and then on the more substituted carbon, I have O with a CH3 on it. And we get that product. Again, if you want to draw it without the hydrogen, that's completely valid. So, and you don't even have to draw the bond, we can just write OCH3. So be careful if you're using an alcohol to add the carbon group to the oxygen, not just an OH. The OH comes from water. One other note that I'll add here is this particular reaction where we're using water is called a hydration. So anytime you add H and OH, just like that, to something, you're adding water, and we call that a hydration reaction. Let's go through the mechanism for this hydration process. And this mechanism can also be applied if you use an alcohol as well. It's the same thing. So we start with our alkene. We have acid and water. And put your pencil down on the double bond. Draw a curved arrow to the acid. We know this step here is called a proton transfer. When you do that, we now go from the double bond to the single bond. The hydrogen goes here where there's already more hydrogen, and we end up with a carbocation on the other carbon that was part of the double bond. At this stage, check for rearrangement. Now in this case we have a tertiary cation. Rearranging it to any of the neighbors is not going to give us anything extra in terms of stability, so we're not going to do that. Now we're ready to involve the water. When we used HX, we added the halogen, or the halide, in the next step. Well, now we don't have any X- group, but we do have water. And water has these lone pair electrons on the oxygen that can act as a nucleophile. So I'm going to draw a curved arrow from that lone pair to the positively charged carbon. Right, the hydrogen, I'm going to leave that implied. I'm not going to draw this hydrogen in again. But now we have a bond to the oxygen of water, and that oxygen still has the 2 hydrogen on it. And it has 1 lone pair. At this point, you should immediately know when you see 3 bonds on oxygen like this, it has a positive charge. This particular step is a nucleophilic attack. Now we're not done here because we still have this charge on our species, which means it's a reactive intermediate. We want to end up with a neutral product. So what we need to do is get rid of that proton from the oxygen. And we need something with a lone pair to act as kind of a base to do that. What we can use is another molecule of water, because there's a bunch of water floating around. So you can use more water. And that will act as a base essentially and take this proton from that oxygen. When you do that, now we're left with the alcohol, plus we've actually reformed our acid, H3O+. This final step is a proton transfer. As we continue to do these types of reactions, different things in the reaction mixture can act as a base. Now in this case, water was pretty much it. But sometimes there will be a variety of things that can do this particular step, and we'll actually start becoming a little bit more generic and just using B with a lone pair to represent something that's a weak base in the solution that can come and take this proton off. So I'm okay if you actually use a real species to do that, or if you just generically use a B in that last step.